Good morning, everyone. We're going to do today the last part of Unit 10, this unit on solution chemistry. And this last part gives you just a little bit of an introduction into acid-base chemistry. For those of you that are going to take AP chemistry at some point, this is going to be a major topic in AP. But even if you're not, it's good to know some of the sort of introductory material that has to do with acid-base chemistry, and it is connected to solutions, which is why we put it in this unit. So let's just start off by talking about some characteristics. Okay, when we say we're dealing with an acidic solution of some kind, I want you guys to understand what that really means on a chemical basis, on a microscopic basis. All that really means is that whatever this solution is contains more H plus ions than hydroxide ions. H plus ions make something acidic. OH minus ions make something basic. So if there's more H plus than OH minus, it will be acidic. Okay. In our last lesson, we talked about what it means to be electrolytic. What are electrolytes? Electrolytes are just free floating ions. Acids contain free floating ions, so they can conduct electricity. Some acids are strong electrolytes, some are weak, but they are all electrolytic. If you add an acid to a base, that's what's called a neutralization reaction, acid plus base. That's just another type of reaction. Okay, now in your notes, which hopefully you have in front of you, there is a picture of this handsome gentleman named Savant Arrhenius. Okay, he was the first scientist to really distinguish certain solutions as acidic or basic. Okay, he was the earliest, the first person to do this. So we've sort of changed his definition, but it's important for you to know it. An Arrhenius acid means something that can give away an H plus ion. Any compound that's, for your purposes, any compound that starts with hydrogen is considered an Arrhenius acid, something that can give up hydrogen ions. Acids typically have a sour taste to them. Think of your fruit juices. They are sour. Okay, lemon juice is sour. Acids are typically sour. They turn litmus paper red. Okay, you probably remember back from 8th grade, or maybe even in biology, acids have pHs below 7. Okay. There is a second, more, I don't know what's the word. It's really a better definition. Okay, called the Bronsted-Lowry definitions of acids. On your notes, again, I always love to include pictures of these scientists. You have two scientists. There's a Danish chemist, Johannes Bronsted, and an English chemist, Thomas Lowry. And these two guys sort of amended the definitions for acids and bases. They made them a little bit more specific. So if you'll notice on the slide in front of you, it says that a Bronsted-Lowry acid is a proton donor. What the heck? Why is the word proton coming in here? I want you to think about something. All right. Look at a hydrogen ion, this H plus ion. How many protons does hydrogen contain? 1. How many neutrons does it contain? 0. If it's an ion with a + 1 charge, let's review what that means. That means it lost the 1 electron that the hydrogen atom did have, so it doesn't have any electrons either. a hydrogen ion is sometimes referred to as a proton because that's what it is. It's just a proton. So Bronsted and Lowry decided we're going to make this definition of acid more specific. We're going to call any compound that gives away, donates its hydrogen ion, its proton, we're going to call that an acid. Now that definition is really not that different than Arrhenius's definition. Bases, however, they're going to be quite different. So let's talk about bases. Okay, it's a lot of the opposite of what we just saw in the previous slide. Basic solutions are things that have more hydroxide ions than H plus ions. Bases are also electrolytic. Some are strong electrolytes, some are weak electrolytes. Okay, they participate in neutralization reactions. Now this is where this gets a little different. Okay, so let's remember what Arrhenius said about acids. Arrhenius essentially said any compound that starts with H is an acid. Arrhenius then said anything that ends at the end of the compound with hydroxide is a base. So something that can give up hydroxide is a base. We're going to change that a little bit in just a second. Bases, rather than being sour like acids, bases are sometimes very bitter. Okay? They are slippery. Okay? If you ever spill a base on, the chemistry counter or whatever, they are, when you're cleaning it up with a paper towel, you'll notice that it is very slick, very slippery. Bases have pHs above 7. And let's look at this new definition here that Bronsted and Lowry came up with. Okay. Bronsted and Lowry said that an acid is a proton donor. Okay, a compound that can give away its hydrogen ion. Well, then they said a Bronsted-Lowry base must be a proton acceptor. And I want to give you an example of why they had to change this definition away from what Arrhenius said. Let me give you an example of a base that you probably have in your home somewhere. Probably in wherever the closet is that you keep your cleaning supplies. Okay, that's ammonia. All right, ammonia is used, for cleaning and things. Ammonia is a base. Now look at Arrhenius's definition. Something that gives up hydroxide, something that ends with hydroxide. Ammonia doesn't even have hydroxide in its formula, but it is a base. So they had to change the definition because this doesn't have hydroxide in it, but it can accept a hydrogen ion. And guys, if that happens, if NH3 were to take a hydrogen ion and bring it into its formula, this is what it would become. Ammonia would accept a hydrogen ion, so there aren't 3 H's anymore, now there's 4, and it takes on a +1 charge. And what polyatomic ion is that? That's ammonium. Okay, so Arrhenius's definitions are sort of the simpler definitions. Bronsted-Lowry is more the more correct definitions for acids and bases. Okay, so here's something that you may be asked to do. Okay, I want you to look at this reaction. First of all, guys, I hope we all know at this point, we're getting towards the end of the year, there is no element A on the periodic table. Okay, I want you to think of A as standing for like any nonmetal. Okay, so when I have HA, that just means some random acid. Okay, now, there's some vocabulary here. Acid and base, we've talked about those definitions. But on the product side, there's something called the conjugate acid and the conjugate base. All right, what I want you guys to notice is what happens to HA, our acid. Think about what its definition is. An acid is a proton or hydrogen ion donor. HA is going to give away that hydrogen. And what does it turn into if it does that? It becomes A-. It gave away its hydrogen. Well, guys, whatever the acid turns into on the product side, after it's done what acids do, it gave away its hydrogen, whatever it becomes is called the conjugate base. Okay? Now, look at what's happening to water. Okay? Now, it seems weird to label water as a base. I mean, water's so neutral. But look at it from left to right. Look at what's happening to it. Is H2O giving away a hydrogen? No, it's not. From left to right, it is accepting another hydrogen. Where did that hydrogen come from? It came from the acid. The acid gave its hydrogen to the base. And what does hydrogen become? When it accepts that hydrogen, it becomes H3O+. Whatever the base turns into after it accepts that hydrogen, that is called a conjugate acid. Okay? So these are some definitions that you need to know. Okay? Here's another vocabulary word, and then I'm going to pause for a second and give you a chance to answer some of the homework questions. If you ever see the word amphoteric or amphiprotic, they mean the same thing. It just means something that can give away a hydrogen ion, but it can also accept a hydrogen ion. And water is a great example. Okay, so amphoteric means a compound that can act as an acid or a base. All right, so H2O is a great example of that. If H2O gives away one of its hydrogens and acts like an acid, guess what it turns into? It turns into OH-. If H2O acts like a base, like on the slide at the top of the slide here, and accepts a hydrogen, it turns into this. Okay. Water is not the only amphoteric substance, but it is one of the most common examples. So guys, what I want you to do at this point is pause the video, go over to the homework questions, and do the first set of questions all the way up to that where you see this chart. It says name each of the following acids. I haven't taught you that yet. You can do everything leading up to that. Okay, so do those problems, check your answers, and then come back. All right, so the next topic to get into is how to name acids, because I hate to break it to you, they have their own naming systems. You know, we learned how to name ionic compounds, we learned how to name covalent compounds. Acids have their own system. Okay, so what I would recommend before we get into this is pull your polyatomic ion sheet out, have that in front of you. That'll be really helpful. Okay, so we've talked about how acids are things that donate hydrogen ions. They release hydrogen ions into the water. All right, how do you recognize an acid? All acids are going to start with hydrogen, all compounds. And there's two types of acids in this world: oxy acids and non-oxy acids, or that second type is sometimes called binary acids. Now think about that first word, oxy acid. Think about what that means. It means exactly what it sounds like: acids that have oxygen in them. Non-oxy acids are acids that don't. Each one has its own set of rules. So let's talk about the second group first, because they're a little simpler. Non-oxy acids, or binary acids, okay? These are acids that don't have oxygen. They're called binary because it's just hydrogen and one other element. That's it, okay? And here's how you name it, okay? And let me pull up an example right here, okay? Like HCl. All right, there's no oxygen in there. It's just two elements, hydrogen and chlorine. It's a binary acid. Here's how you name these. If it's a binary acid, you start with a prefix hydro. Then it says anion root. Okay, well, the anion is chlorine, so the anion root is chlor. And then it's ic acid. So instead of calling this hydrogen chloride, we call this hydrochloric acid. Hydrochloric acid. Okay, look at this one. Don't worry about the fact that there's a subscript of a 2. That doesn't change anything. It's still just two elements. It's hydrogen and it's sulfur. Same rules apply. Hydrosulfuric acid. Hydrosulfuric acid. Okay. Now this one is a little tricky because you might say, well, wait a minute, that's not just two elements. And you're right, it's not. But does that compound have oxygen in it? No. So technically this is classified as a binary acid. And guys, I wouldn't give you one like this on a test or anything. I'm just sort of throwing it up there for fun. Look at your polyatomic ion sheet. This is not one of the polyatomics I had you memorize, but what is CN? It's cyanide. So we're going to use the naming rules in front of us. This is hydrocyanic acid. Again, I wouldn't throw one like that on the test. I just wanted to put that up there for funsies. Okay, so that's binary acids. What if it's an oxy acid, meaning an acid that does have oxygen? And for our purposes, guys, this is going to be acids that most of the time have one of our polyatomic ions in it. Okay? So here's the deal. This is when it's really important to remember the name of that polyatomic ion. Okay? So oxy acids are hydrogen joined to one of our polyatomics. Okay? Like, let's say chlorate. Hydrogen and the polyatomic chlorate are joined together. So look at the rule here. It says change the suffix ate, like chlorate, to ic. All right, so here's the deal. If I have hydrogen and chlorate put together in an acid, I'm not going to call it chlorate acid. I'm going to call it chloric acid. Okay. If the polyatomic ion ends in ite, like chlorite, I'm not going to say hydrogen chlorite, or I'm not going to say chlorite acid. Look at the rule here. I'm going to call it chlorous acid. So let's do a couple together. I'll talk about the sulfurous in just a second. Okay, so let's look at this one. Again, ignore that subscript of 2. It's not going to change the name. Hydrogen is joined to, look at your polyatomic ion sheet. What polyatomic is that by name? That's chromate. So according to this rule, this should be chromic acid. All right? You'll notice, guys, I'm not putting that prefix hydro in these names. That's only for binary acids. That was on the previous slide. Oxy acids don't have that hydro prefix. So this is chromic acid. All right. Hydrogen joined to, look at your polyatomic ion sheet. What's the name of that polyatomic? That's perchlorate. 8 turns into ic. So it's perchloric acid. Okay, let's do one more. Hydrogen joined to, what's the name of that polyatomic? That's nitrite. Ite goes to us. This is nitrous acid. Okay, and my students years ago came up with this little rhyme to remember this naming system. 8 goes to ic, ite goes to us. It's stupid, but it might help you remember. If you ate something gross, it makes you feel sick. If you get in a fight, you need us. I know, it's dumb, but maybe it'll help you remember that. Sulfuric and sulfurous, you got to be a little bit careful. Some people might be tempted to say, like, if it's sulfate, a lot of people are tempted to say sulfic acid, or if it's sulfite, you might turn it into sulfus, but just ask yourself if does that sound right? It's sulfuric, sulfurous. Okay. You also need to be able to go the other way. Like being given the name of an acid, you need to be able to write the formula as well. Not just go from formula to name, but name to formula. And I want to do one of these with you. I'm going to do this guy right here, carbonic acid. And I want to talk through the thought process here. Okay. I know it's an acid. I see the word acid. So immediately I know, okay, hydrogen is the first element in that compound. Now look at the word carbonic. I don't see a prefix hydro. It's not there. Think about what that means. There's no hydro prefix. That means it's an oxy acid. And in your mind, I want you to think, okay, that's one of my polyatomic ions, but which one? Well, look at the ending. It ends in ic, which means it came from a polyatomic that ends in ate, carbonate, which is CO3, and it has a -2 charge. What is hydrogen's charge? It's in group 1. So it's +1. Guys, acids are treated very much like ionic compounds in that you have to think about your charges and do the swap and drop. So let's think about what the formula for carbonic acid is going to be. H2CO3. So I want you to sort of pause the video here, take a second. These are not in your notes, so just kind of do them on a separate sheet of paper or out in the margins if you want. I want you to come up with the formulas for the rest of these acids, and I'll start writing up the answers here. Okay, how'd you do? One that tends to confuse people a little bit is this guy right here, dichromic acid. Some people see that prefix di and think, wait, that that looks like a covalent compound. Why are we having those prefixes like di, tri, tetra? If you look at your polyatomic ion sheet, we have a polyatomic ion called dichromate. Okay, so that di is just coming from the name of the polyatomic ion. That's all. So what I want you guys to do at this point is pause the video. There are 2 charts in the homework questions that I want you to complete where you're naming and writing the formulas for various acids. Okay, so complete that, check your answers, and then come back and we'll finish this part up. All right, guys, so the very last part of this section and this unit as a whole involves a little bit of math, okay, where we're going to actually calculate what the pH of a certain solution is, or what is the molarity of the hydrogen ion concentration. What's in front of you, you probably know and have since middle school or even earlier. The pH scale goes in general from 0 to 14. 7 is neutral. Below 7 is acidic, above 7 is basic. I want you guys to know that there are pHs that exist below 0. There is such a thing as a negative pH. That just means a solution that is like wicked acidic. Okay, and there are pHs above 14 as well. That would be something that is super basic. So get out your calculators, right, if they're not out already. Just for your information, that abbreviation, pH, actually does stand for something. It stands for potential of hydrogen. Okay, pH is essentially a measure of how much hydrogen ion is in the solution. Okay, it's a way of expressing the concentration. Okay, if you see brackets around something, like see how in this statement here, there's a set of brackets around H+. Brackets mean molarity. Okay, the concentration of whatever's inside that set of brackets. There's a formula here. Now, I don't want any of you to freak out. I know everybody is all in different levels of math. Some of you have worked with logarithms. Some of you haven't. Some of you are very comfortable with them. Some of you are not. Don't worry about it. All you need to be able to do is to push the button log on your calculator, and I'll show you where that is. Okay. So let's say you are given a molarity of H+, and the question says calculate the pH. All you literally do is type in negative and then look at your calculator. Right next to the number 7, there's a button that says log. Okay, that's a logarithm base 10. So you would type in negative sign, hit the log button, and type in that molarity, whatever it is, hit enter, and that would be your pH. That's all there is to it. Okay. If you have, just so you guys understand this, if you have a high pH, like let's say a pH of like 13, okay, that's pretty high on the pH scale. A high pH means we're talking about a pretty basic solution. It's very basic. That means a low hydrogen ion molarity. Think about it. If something is very basic, there's not going to be a lot of H+ floating around. There will be, however, a lot of OH- floating around. Okay? Now, this one you may not be familiar with. There is a pH scale. There's also something known as pOH, but it's the exact same thing. It's just the opposite. Potential of hydroxide. Okay? And it has a very similar formula, except instead of doing the negative log of the H+ molarity, it's negative log of the hydroxide molarity. Okay? The more H+ ions there are, the smaller the concentration of OH- will be. Here's another helpful formula. pH and pOH for any solution will always add up to 14. So let's say you are given, and I'm going to do an example with you in just a second. Let's say you're given a molarity of OH minus. You type it into that first equation in red there, negative log, and you put in that number, and what comes up in your calculator is a pOH equal to 5. If I then said, well, what is the pH? pH plus 5 equals 14. That must mean the pH is 9. And think about that. If the pH is above 7, it must be a basic solution. So, as I said before, guys, here is that log button right there on your calculator. Okay, if you don't have a TI calculator, it's somewhere, but look for log. Okay, so what about if you're given a pH or a pOH and you're supposed to go backwards? Again, some of you are more comfortable with logarithms than others. All right, so I wanted to just kind of go through a problem with you. So look at this example. It says an acidic solution has a pH of 4.9. Calculate the concentration of H plus ions. Well, here's my formula. Negative log of H plus. Okay, the pH is 4.9. Sorry, my handwriting's a little messy. Some of you are comfortable, and this is probably not the right mathematical term, undoing a logarithm than others. Okay, I'm going to show you what to do. First of all, guys, bring the negative over to the 4.9 side. So let me rewrite that. Negative 4.9 equals log of H plus. You can just bring that negative sign over. That's fine. How do you undo a log? Well, on your calculator, guys, hit second log. And what's going to come up in your calculator is going to be something like this. 10 to the power of, and then it's going to wait for you to put something in there. Okay? It's waiting for you to put an exponent in. And what you're going to put in there is negative 4.9. Okay, so I'm going to do that right now on my calculator. 10 to the power of negative 4.9, hit enter, and I'm going to round to two significant figures. So I get this. The H plus concentration is equal to 1.3 times 10 to the negative fifth power, and it's a molarity, so I'm going to put a capital M. Final answer. Okay, that's how you undo a natural log if you need to do that. Okay, so let's do one problem together and then we'll call it a day. If you look at the chart at the very end of these homework questions, I want us to look at line number 7. Okay. So if you'll notice, in this chart, you're either given the molarity of H plus, the pH, the molarity of OH minus, or the pOH. And they want you to fill in whatever's missing. Okay, so let's look at line number 7, where you are given this piece of information. You are given the molarity of OH minus. Okay? The order in which you do this doesn't matter. I personally think the easiest thing to do next would be to solve for the pOH, which is negative log of that molarity. Okay, so I don't have to do the second log in this one because I'm just typing it in straight. Negative, hit the log button of 0.3, enter, and this is what I get for the pOH. It's a really small number. And let's go 3 significant figures. So 0.523. And pHs and POHs have no units. You lucky ducks, you don't have to worry about it. Okay, so there's my POH. Next thing that we should probably solve for would be the pH. Think about this formula that we have on the other side of your, other side of your notes. Those two quantities always add up to equal 14. So, pH plus 0.523 equals 14. So, what must the pH equal? 14 minus that number, and we'll get 13.5. Okay, so let's pause here and fill out the final column over on the far right. If the pH is 13.5, is this an acid or a base? It's a pH above 7. It's definitely basic. Okay. Last part, we've got to find the the concentration of H+. And this is doing that process I was showing you just a moment ago. So I have my pH. What I don't have is the molarity of H+. Okay, bring that negative sign over to the other side. You can do that. That's perfectly acceptable. All right, and let's practice this. So go into your calculator, second log. And what you should see pop up on the screen is 10 to the power of blink, 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 and it's waiting for you to put in that exponent, negative 13.5. And I get a very small number. The H+ molarity is 3.16 times 10 to the negative 14th molar. Final answer. Okay? That's all there is to it. Okay? It's just using different formulas. So that is the end of acid-base and the end of the solutions unit. I hope you have enjoyed it as much as I have. I look forward to starting the next unit with you guys, so have a wonderful day. Bye, everybody.